The reading about these topics are found in chapters 1 and 2 of the 5th edition. Yeah, any questions? So everything is clear or everything is unclear? Okay, are you okay? Okay. Okay, let's move on to the next lecture. We are going to finish the course today. Okay. So this is the first real lecture, okay? And I really advise you to concentrate on this lecture because it will come haunting you every day. You will need this lecture for the rest of your, not your life, but for the rest of this course. Okay, so can we concentrate a little bit, or do you want like 1 minute break? Right. 50 seconds left. Okay, time's up. So, lecture 2, basics of algorithm analysis. So, in this lecture, we will learn techniques that will enable us, when we look at an algorithm, we know that this algorithm is going to be efficient or not. So far, we have talked about the 3 characteristics of an algorithm. Definiteness, finiteness, and efficiency. So this lecture is really about efficiency. So this lecture will give us the tools in order to say, is this algorithm efficient and under which conditions? For example, to give you some motivation like about this topic, so I'm talking in example 1, I'm talking about something that I call absolute efficiency. So what's absolute efficiency? So let's think of an algorithm A that solves some problem P. We don't really care what the problem P is, and we don't really care about how A is written. Okay? So, and we want to know whether or not A is efficient. So what I'm saying here is I run algorithm A on some input, okay, on some input set. For example, the algorithm that takes the that finds the maximum of the 3 integers. An input to it is 112 or 114 or 556 or 10, 11, 12. These are all inputs to that algorithm. So all together they form what we call the input set. So this is what I'm saying here. Let's say that we have an algorithm A that solves some problem P, and the input set of algorithm A, we refer to it as S. Okay? And then what I'm saying is run it on some inputs from this set S and measure the execution time the execution time of the algorithm, because efficiency is linked to time. If we said if the algorithm can solve the problem in manageable time, then it's efficient. So I'm running algorithm A on some inputs from the set S, and we are measuring the execution time for every input. And then what I'm saying is algorithm A is efficient over the input set S if it has a small average execution time over S. Okay? The problem with this approach is, we can only say that A is efficient or not only for those inputs that we have used in the measurement. So if we have used with the input 115 or 346, then we cannot say it is efficient for the input 11, 12, 1000. Okay? So measuring the execution times for few inputs or several inputs is not going to tell us if the algorithm is efficient or not. Now, the only way that we know an algorithm is efficient is if we can execute the algorithm with every possible input. Okay? Now, this is not possible because the size of the set S is huge, and we don't have time. We cannot try a program in the general case. I'm not talking about small program. In the general case, we cannot execute a program for all possible inputs. It's just impossible. So that's why this way of analyzing efficiency is not suitable either. So the first one is not suitable because the results that we obtain for a subset of the input cannot be generalized to the rest of the set. And the second way is not suitable because simply it's not possible to execute a program or an algorithm for all possible inputs because their number is astronomical. Okay? So here I'm just trying to tell you, we're trying to get to this point where we talk about asymptotic complexity. Okay, so that's motivation 1. Now motivation 2, so the first one we talked about how do we know that A is efficient, A by its own. Okay, we're not comparing A to another algorithm. That's why I called it absolute efficiency. Okay, we use the word absolute when we are talking about an entity on its own. Okay, but when we talk about two entities together, then we use the way relative. So for example, a book can be, if a book costs $1,000, that's absolutely expensive. That's an absolute value. If a book costs $30 and another book costs $20, then the one which costs $30 is the book costs $20, then the one which costs $30 is relatively more expensive. Okay, it's not really expensive, but comparatively with the other book, it's more expensive. So we have absolute when we say this algorithm is efficient, is not efficient, and we have relative when we say this algorithm is more efficient than this algorithm. Because this is what we will see. We will see certain problems like the sorting problem, okay? And we will see different algorithms and we will compare them. We will say that this algorithm for the sorting problem is better than this algorithm for the sorting problem. And sometimes we see just one algorithm and we just argue about this algorithm in an absolute way. So that's the difference between absolute and relative. So how can we say that A is more efficient, that some algorithm A1 is more efficient than algorithm A2? By the way, we can only compare algorithms that solve the same problem, okay? If an algorithm is solving P1 and another one solving P2, I mean, we cannot really compare them because they are not doing the same thing, okay? But algorithms that solve the same problem, okay, we will see an example right now. These are the kind of algorithms we try to compare to each other. So we have A1, A2 solving some problem P. How do we know which one is more efficient? So we can try again what we did in absolute efficiency. We can run them on few inputs and get results. But again, the results that we get are exclusive to this subset of inputs that we have measured with. Okay, we cannot generalize the results to the rest of the input set, and running them on every possible input also is impossible. Okay, because they're potentially there's an exponential number of different inputs. So this is basically saying almost the same thing. The only difference is the other one we are talking about one algorithm, and the other one, the first one we're talking about one algorithm, and the second one we're talking about two algorithms. So if we have two algorithms, I mean, I'm going back to this point here in slides. Now let's say that somehow we are able to execute these two algorithms for every possible input. Let's assume it's not possible, huh? It's not possible, but let's assume. Let's assume that the problem is small, or the input space is small. Let's say there are only 1 million different inputs for this program. Let's say, and we find two algorithms, A1 and A2, that solve this problem for us. So we execute every one of them for each input of the input set, i.e. 1 million times 1 million times. So which of the two is better? Is it the one with the shortest average execution time? Is it the one with the shortest largest execution time? Or is it the one with the shortest smallest execution time? Now each algorithm has got a shortest execution time, which is the smallest time it's going to take. And because, I mean, programs, they will not take the same execution time for all inputs. Some inputs will cause loops to be executed, some of them will cause loops not to be executed, etc. To give you an example about that, I mean, just assume a program which program P. Can you see anything? Or is it upside down? Right, so I need to do it this way. No way. Okay. So we have program P. Come on. Program P. Do you see it now?
Yes.
Okay, so it takes input X, and program P takes input X, says if X is greater than 0, then X plus plus. Else, for I between 1 and a million, do something, and loop, and then end if. Okay, I'm sure this is not the best of handwritings in the world, but I'm just trying to show an idea. So that's a program P. It says if X is positive, do an increment operation. If it's not, do this huge loop. So if the input is 5, we are going to execute this part. If the input is -5, we are going to execute this part, correct?
Yes.
Okay, so this is an example of a program whose execution time is going to be different depending on the input. If we give it a positive input, the execution time is very short. If we give it a negative or 0 input, its execution time will be very large. Okay, so that's what I mean. That programs, they have different execution times depending on the input they take. Okay, so again we have two algorithms, A1 and A2, and we want to measure their execution times. So we execute every one of them for every possible input. We said between quotation marks that we can do it. So which one is more efficient? Is it the one with the shortest average execution time, the one with the shortest largest, or the one with the shortest smallest? In algorithm analysis, the one with the shortest smallest execution time does not matter a lot. The one with the shortest average execution time sometimes matters. The one with the shortest largest execution time is the one that we usually look at. What we are interested in is how the algorithm is doing in its work. We call this the worst case, okay? So the program that I have shown you now, which takes input x, and if x is positive, it executes a simple statement. If x is not positive, it executes a huge loop, okay? So we say that the worst case of this program is when the input is what? You're not following? So what's the worst case of my program here? Yeah. When x is less than or equal to 0, this program is in its worst case. Thank you. Okay? So this is what it means. Okay, let's see something more. So this is just a summary. We want to know if a particular algorithm is efficient in solving the problem. This is absolute efficiency. We want to know, that's one. And two, we want to know if an algorithm is better than another algorithm. So worst case behavior. Do I have this? Okay. For example, focus on this algorithm with me. Can you see it on screen? Is it big enough?
Yes.
Okay. So this algorithm takes as input some array A and some integer x. And what this algorithm is doing is it's executing a loop, and then depending on the if statement, it either executes a loop or it executes an increment or an assignment statement. So if we think about this program, I mean, what causes this program to have the largest execution time? That was the question, by the way. Huh? Again, okay. So this is a program in front of you, and I've described the different parts of it, and I'm saying what causes this program to have the largest execution time, or a large execution time. So if x is greater than 0, it takes more time than when x is less than or equal to 0. Because when x is greater than 0, there is a loop executing, correct? Right. The other thing that also causes this to have a large execution time is the value of n. Okay? So if n, which is the size of the array, so if n is 100, that's going to take more time to execute the loops than when n is 10, for example. Okay? Is this clear?
Yes.
So I am saying that in this algorithm here, it is the number of how much time it spends at runtime is influenced by the value of n, because n is going to influence how many times the loops are going to iterate. Okay, the loop iteration here is not constant; it depends on the variable n, in this case, and also in this case. Okay, so the loop iteration depends on n. This is why a larger n is going to cause more time, and also it depends on the value of x, because depending on this value, we either execute a loop or not. Okay, so when we talk about the analysis of algorithms, we are interested in the worst case, like what is going to cause this algorithm to have the largest time. And this example shows you that one way, or one of the things that we should look at is the iteration, the maximum iteration number of the loops. Like this loop in line 5 and the loop in line 10, their maximum iteration number is depending on the variable n. So that's why we look at them, and also the worst case behavior of the algorithm also depends on the conditional statements. If one part of the conditional statement executes lots of statements, or an expensive statement like a loop statement, and the other part of the if statement executes very few statements, then the worst case is we are going to see it when the alternative of the conditional statement that contains the expensive statement is executed. Okay, so there are two ways to look at in this code. The maximum iteration number of the loop, if it depends on an input variable, and the conditional statements when they are not balanced, when they in one part they contain a lot of code or some expensive code, and the other part they don't contain much code. So that's a note on worst case behavior. We are going to revisit it at the end, but I wanted to mention it now so that you feel what it means along the lecture. Okay, so now we will see an example of two algorithms that solve the same problem, but they have different execution times. I am using the word execution time. I haven't yet used the word asymptotic complexity. We are moving towards asymptotic complexity, that we will see what it means. So for now, we want to write an algorithm which basically solves the problem of summing up the natural numbers from 1 to n. So we want to write an algorithm that gives us the sum of the numbers from 1 to n. So if n equals 3, then it should give us the sum 1 plus 2 plus 3, which is 6. If n is 4, then it should give us 10. 1 plus 2 plus 3 plus 4 equals 10. Okay? So we want to write an algorithm that will give us this kind of sum. Okay? Now, using our mathematical knowledge from arithmetic series, we know that this sum equals that amount. Okay? From 1 to n, the sum of the numbers equal n times n plus 1 over 2. That's a simple rule. Now, we are going to see two algorithms. One that uses this rule, and one that does not use it. Okay? So, algorithm A1, the top one, uses the rule. It takes as input an integer n, and the objective is to compute 1 plus 2 plus 3 plus 4 blah 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 until plus n. So what it does is it uses the rule straight away. Whoever wrote this algorithm knows the rule. So he or she wrote it directly in this figure. Okay? Huh? A question? Is that a question? Okay. So that's this algorithm uses the rule. Now, the other algorithm does not use the rule. The other algorithm, let's say I am trying to write this, but I don't remember. I don't remember what the rule is. I don't know what's 1 plus 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 equal. So what I am doing plus equal. So what I am doing, I am computing it myself. Okay? So what I am saying is, I will. So it's the same one. It takes the same input. However, in this case, I am going to write the sum myself. Or to compute the sum myself. So I'm saying that from I to n, from 1 to n, sum equals sum plus I. Okay? So sum is a variable. It's going to contain 1, and then add to it 2, and then 3, etc. Basically, these two algorithms are like two people. Someone who knows the rule. I mean, we pick them up in the street and we ask somebody, what is 1 plus 2 plus plus until plus 100? And one of them knows the rule, so he will just say it's 100 times 101 over 2. And he or she computes it straight away. The other one will start using his fingers trying to compute 1 plus 2 plus 3, etc. because he does not know the rule. So these two algorithms are pretty much like two people, one who knows the rule and one who does not know the rule. Now, we want to know which of these algorithms is effective. I mean, do you all agree that these algorithms are equivalent? They do the same thing. Okay? Now, which of the two is more efficient than the other? Right. So the first one is more efficient.
Yes.
Yeah. Because it uses. I mean, it doesn't. Okay, it's more efficient. We will say something and we will explain it later. The first one takes constant execution time. Okay. By that, what do we mean? Is the number, the time that it takes does not depend on the input. So, if we give it n, input n equals 100 or 1000 or 1 million, it will always find the value of the sum in the same time, almost. Now, for the second algorithm, if we give it 1000, the loop is going to repeat the step 1000 times. If we give it the input 1 million, it will repeat the step 1 million times. Okay? So the first algorithm, the execution time of it does not depend on the input. The second algorithm, its execution time actually depends on the input. Okay? Now, when we say execution time, we really mean the number of steps. Okay? Because in this case, in this algorithm here again, the first one, the top one, when we execute it, I mean, think of yourself as a CPU. What you're doing is you are defining sum as an integer, and then you are performing a multiplication and an addition and a division and an assignment statement. Okay, this one statement has a multiplication, addition, and division and assignment, and then you are making a return. So the number of steps here is the same, whether or not n is 100 or 10 or 1 or 1000. It's always going to be the same number of steps, right?
Right.
In the second one, it's going to be different. So when we say time, we really mean runtime steps. This is different from the number of steps of an algorithm. Like in the cake algorithm, for example, there is step 1, do something, step 2, do something. These steps are for describing the algorithm, okay? They are not the runtime steps. Step 1, do something, step 2, do something. These steps are for describing the algorithm, okay? They are not the runtime steps, okay? Here we are talking about runtime steps, okay? When the algorithm starts executing, then these steps are going to happen. For example, the loop, this is one step in terms of description, okay? But in runtime, it's going to be n different steps. So let's not mix up. It shouldn't be mixed. It's very obvious. So when we talk about the description of an algorithm, we have descriptive steps, like step 1, put sugar, etc. But during execution, we are talking about the real number of steps. So again, algorithm A1, the top one, the number of the execution time or the number of runtime steps is constant. By that we mean it does not depend on the input. The input changes, the number of steps stays the same. The second algorithm is not constant. The number of steps is going to change if the input also changes. Actually, the second input is linear, and we will see. So algorithm 1 computes the result in a constant number of steps. So I'm saying that I'm using the notation T of A1 to refer to the execution time of algorithm 1. So this means execution time of algorithm 1. And I'm saying it's equal to some constant beta 1. Okay? Because it doesn't depend on the input. Okay? And for algorithm 2, it actually depends on the input. If the input increases, the execution time is going to increase as well. Now, can somebody tell me what is beta 1 in algorithm A1? What is beta? Huh? Beta 1. I mean beta 1. Beta 1.
Constant.
Yeah, the constant. How do we visualize the constant here? What is the constant in algorithm 1?
Two. Number 2. Yeah. So the formula.
2?
Yes.
Okay, let me ask the question for the second algorithm. We said the second algorithm, the time has got this shape. Okay, so T A of 2 equals alpha to n plus beta 2. Okay, let me return to this question in a while. So memorize with me now these equations. So the execution time or the number of steps of TA1 of algorithm A1 is beta 1, and the number of steps of algorithm 2 is alpha 2 times n plus beta 2. Now these two are just equations of straight line. Okay, I mean you remember the straight lines, y equal x or y equal ax plus b. Okay, so this is just like, this is the y equals a constant, so this is y, and this is the constant. No, sorry, this is not y equals x. I meant y equal, for example, c, which is a constant. Okay, so this is c, and here this is y, and this is the execution time is changing with respect to value n, so n becomes y, and this is the execution time is changing with respect to value n, so n becomes the x, alpha 2 becomes the A, and beta 2 becomes B in this equation. Okay, so we have a value y here, which changes with respect to x with some proportion A, and there is an offset B. So this is the line this is the equation of a line y equal ax plus b, which is similar to that, and the same here. So if we try to plot this, so algorithm A1 is going to be this. So this is the number of steps, which is t of ai, either ta1 or ta2. This is the number of steps, and this is the input size, which is n. Okay, so the execution time, the number of steps of algorithm A1 stays constant. So if n increases, it doesn't increase, it stays the same. You see that? Okay, but the execution time, or the number of steps of A2, increases with time. Okay, so this is constant. This has the equation. This has the equation t of A1 equals beta 1, and this one has got t of A2 equals alpha 2 times n plus beta 2. Okay, so this is a proper line. I mean, it has a slope, etc., and this is a horizontal line because its equation is y equals some constant. Now, I have drawn. Do I have a rubber here? No. Okay, I just remove these kind of things now. Okay, so I have drawn two different shapes. One, as you can see in the left hand side, and one as you can see in the right hand side. Are they both correct, or is one correct and one is not? Or, I mean, what do you think? So, what's your answer?
Maybe both is correct.
Both are correct.
Yeah.
So, in which case does the second one happen? I mean, the right hand side. In which case? Yeah, are you going to tell me by tonight or what? Oh, my question. My question is, in which case do we see the one on the right hand side? I will unfortunately have to write. Do you see all four x's?
Yes.
Right.
Yeah.
Okay, so let's say algorithm 1 is something like that. It takes input n, and then what it does is it says, for example, x plus plus y a plus plus b plus plus and until z plus plus. Let's say it makes 26 increment operations, and a2 does something for I in 1 to n. What it does is x plus plus. Okay, so this algorithm makes for 26 increment operations. This one makes how many increment operations?
What?
Wrong.
No. N.
Right, n. Now, what is the execution time here? Is it constant or is it not constant?
Not constant.
What's the definition of constant again?
Constant don't change in the program.
Okay, it doesn't change if the input changes, yes?
Yes.
Now, if we change n here, is this number 26 going to change?
No.
So is this constant or not?
Constant.
Constant. Is this constant here?
No.
Now, if we try to plot these, this is the number of steps, and this is the value of what? What do we have here? N. So, when n is 1, how many steps do we have here? Okay, let's not call them steps. Let's call them, for example, number of increments. Let's ignore what happens inside the loop for a moment. Let's ignore the conditions and the increment of the I, etc., because these are all operations. But let's ignore them. Let's just focus on these. Okay. So if n is 0, how many of these do we have?
1.
How?
0.
Okay. If n is 1,
1.
and if that is 2, that's 2, etc. So that's the line for which algorithm? That's the line for which algorithm? A2. Now, if we try to draw line of algorithm A1, how do I draw it? Where is it going to be?
And 26, and it will be straight line.
Yes, horizontal line at coordinate 26 here, right?
Yeah.
So that's A1. This is exactly what we have seen in the second case. Okay? I mean, let's have a look again. In this range here, in this range, the number of steps of algorithm A1 is larger than the number of steps of algorithm A2, correct?
Yes.
And after the intersection, the number of steps of algorithm A2 becomes larger than the number of steps of algorithm A1. And that's just this case. Before this intersection here, the number of steps of algorithm A1 was larger. Okay? But after this, the number of steps of algorithm A2 is larger. But in this algorithm here, A2 was larger all the way through. Okay? For example, I mean, can you tell me how do we get this? How do we get this, the leftmost one? I mean, I've shown you an example on how to get the rightmost. Can you show me an example how to get the leftmost? Okay, it's not very hard. It's very simple. We can use the same trick. We can have algorithm A1, and it has A++ and B++. Okay, and then we have algorithm A2, and let's say it has C++, D++, E++, and a for loop. A for loop that depends on n, and which has an increment operation like F++. Okay, so when we draw A1, it's two steps, so that's going to be A1. Here is 2, and A2 is going to be 3 steps, and with a slope of what's the slope of this line? Is going to be, because we have when n is 1. There is only one statement that gets executed. So that's 1. When it's 2, that's 2. So the slope is really like 45 degrees here. I mean, it doesn't matter if you don't understand what I'm saying here, but it's what you have to understand is this shape, and that we can have this kind of case and this kind of or that kind of case. Now, what's important about, like, why do I show you the two different versions? Is to stress one point. This point is, it really doesn't matter if they intersect or not, because what we care about in our analysis is how the algorithm is doing when the input is large. I mean, remember what we said about the worst case? We said when we compare the efficiency of two algorithms, we look large. I mean, remember what we said about the worst case? We said when we compare the efficiency of two algorithms, we look at the worst case. Okay, and we said what the worst case means. We said we look at the loops and we see if they depend on an input variable, then the largest values of this input are going to cause the worst case behavior. We said that, right? Okay, so this means that what's happening in this region here is not really important, or this region, because in this region n is small, the input is small. What really matters is what really matters is what's happening in this region here, is when n is towards infinity. Okay, this is what matters. In other words, this algorithm here, A1, now in this small range here, which algorithm is more efficient? The algorithm which is more efficient is the one that has the smaller number of steps. Okay, because it comes. Okay, so A2 is more efficient because it has smaller number of steps. So in this region, A2 is more efficient. But then in infinity, which one is more efficient? Okay, so this is all we care about. Okay, so we say that A1 is more efficient than A2 because what really matters is that. Okay, is when n is very, very large, because the difference in their efficiency here is nothing, because when n is small, computers are very fast, and if one is faster than the other here, we are not going to notice this difference much, because computers are fast. And when n is small, this difference is going to be very small compared to how fast computers are. Yes, thank you. Now, in this region here, when n is towards infinity, we are going to notice the difference between A1 and 2. Okay, that's why we concentrate on this region. Back. In this part, A1 is always more efficient, so it's not really interesting here. But we know that A1 is always more efficient. But in this part, A1, at the start, it is not more efficient, but towards infinity, it is more efficient. Okay? After that, we're going to stop here so that we don't get into something new. So let's just recap. So what we have seen is we said that we want to do the analysis of algorithms. We have talked about absolute and relative efficiency. So is an algorithm efficient, or is it efficient with respect to some other algorithm that solves the same problem? We have seen how when we do the analysis of algorithms, how do we think about them? How do we think about the worst case? We have seen an example of two algorithms that solve the same problem. One has a constant number of steps. Another one has a linear number of steps. Right? And then we said that what matters in the analysis of algorithms is when the input is large, which causes the algorithm to be in its worst case behavior. So what we really want is when the input is towards infinity, causing the differences between the algorithms to be very large to observe. Okay, so that's what we have.